review. Like I said, the first section is kind of more I would classify as the pseudo-important stuff. I tweaked the nomenclature slide a little bit. We've got all of the important functional groups highlighted in black with their rankings, highest to lowest, and all the extra little names that go along with them. Whoops, except for the amines. And then the nomenclature rules on the right are slightly tweaked. Find your longest carbon chain that contains the highest priority group, okay, and kind of work from there. But ultimately, it's the same rules that we've been seeing. It's just applying them again and again and again, okay? I didn't do an extra slide for nomenclature of the arenes, though technically they have a slightly different nomenclature system, so it doesn't quite match or mesh with this a little bit, okay? Resonance and mechanisms. Guaranteed you will see a mechanism on the exam, okay? I promise. I've already tested you on a bunch of mechanisms from the older stuff, and then in the newer stuff, most of the mechanisms were really difficult, really except for one. Which mechanism was probably the easiest? See what you guys come up with. Acid base is old school, so we won't count that. Working with the aromatic rings, the EAS chemistry. Okay? So you can almost guarantee that you are going to see some EAS mechanism where you're going to be expected to draw everything out. Okay? So prepare for that because you know what's going to happen. Okay? Resonance is a major portion of organic chemistry. It's what determines a lot of the different reactions, where things react. All comes back to resonance, so you can expect to see a lot of resonance type questions as well. Okay? Resonance has an extra little special place as well because in the EAS reaction, or the mechanism for that one, you have to draw resonance structures. Okay? And then deciding where the individual electrophiles end up substituting on the ring is dependent on resonance. Okay? So you can see already that within the new material just on its own, lots of resonance, lots of mechanism stuff. Okay? Resonance still applies to all the older stuff, so you can still expect to see resonance questions show up in there. Okay? Remember, when you're dealing with resonance and mechanisms, the whole point is to show the flow of electrons. So you're going to start your arrow at a source of electrons and show where those electrons end up going. Okay? If you're making a new bond, the electrons are going to go to an atom. If you're making a new sigma bond, you're going to take the arrow and end it at an atom. If you're making a new pi bond, you'll move the arrow to the new bond space where the electrons of that pi bond show up. Okay? Kind of makes sense? So what we're looking at with our flow is atom to bond, bond to atom, and then if we can cheat with resonance, we can sometimes do bond to bond. Okay? Questions with our resonance and mechanisms? Okay. Acid-base strength. Okay, so you've continually seen on pretty much every exam questions about defining your Bronsted-Lowry acids and bases, your Lewis acids and bases. Those we could then apply to nucleophiles and electrophiles. So being able to define and rank your acids and bases and electrophiles, nucleophiles, all of that is going to be an important role. Not only should you be able to define them, but you then need to be able to apply that knowledge to a new structure. Okay? That's where ranking things can come into play. Okay? So being able to look at your acid-base strength, how can you make something more acidic? What changes to the structure makes something more acidic? What changes to the structure makes something more basic? Okay? Those ranking systems play an important role when you're dealing with carbonyl chemistry. They're going to be even more important when you move into biochemistry. Okay? It may not be emphasized, but they're going to play a large role. Okay? In general, what's the definition of your Bronsted-Lowry acid? So if we're looking at a Bronsted-Lowry acid, we're looking at a proton or hydrogen donor. If we're going to try and decide if it was superreactive, how would we do that? We look at the conjugate base. Okay? And that's where all of these rules come into play. Size, electronegativity, induction, resonance. It's all looking at the conjugate base. So when we look at the conjugate base, for something that's a strong acid, our conjugate base has to take the electrons away. Those electrons need to be stabilized. Okay? Which is why when we're looking for a stronger acid, we expect something that is less negative. Okay? We've stabilized those electrons in the conjugate base. When we move over to the base definition, what's the definition of a Bronsted-Lowry base? It's a proton acceptor. That definition is a bit obnoxious because we won't know if it can act as a proton acceptor until after the fact. Okay, so what would we look for in a proton acceptor? We want to look for electron density. Okay, so I heard someone say it, a negative, lone pairs. Okay, all of those are good things to key off on Bronsted-Lowry bases. And since what we're looking at is the electrons doing the reaction, we don't have to look across a reaction arrow. We can just evaluate. Does the structure have more negative charge? The more negative it is, the more likely it will act as a strong base. Okay? It doesn't always hold true, but that's pretty close. Okay? And then we can then go through all of those rules and apply them in those particular circumstances. Okay? When you're applying each of these, trying to evaluate either the stability of the conjugate base or different base strengths, you want to make sure you're comparing the same thing. Okay? So don't start evaluating size if there's something else that's more important before that. Okay? For instance, if we had, let's look at the bases because they're easier for me. Let's say we had H minus versus can I come up with an example on the fly? I may not be able to come up with an example on the fly. Shoot. Yeah, maybe we'll come back if we got time and I can try and think of one a little bit better. I don't want to delay too long. Okay. You got questions on the acids and bases? Okay. The simplest approximations when we're dealing with our acid-base strength, we can go through and just add that hydrogen to a single element or just evaluate that single bond. So we can look at hydrogen to chlorine, hydrogen to oxygen, hydrogen to nitrogen, hydrogen to carbon. Why do we not really need to worry about any other elements? Because it's not organic chemistry. When we're dealing with organic chemistry, those are our primary ones we're concerned about. We can expand that chlorine a little bit and expand that out to the rest of the halogens. Okay? But that was one of the nice things with organic chemistry. We simplify and only look at certain elements. We don't have to worry about all the other ones. Okay? Halogens pretty much will only act as acids. Okay? If we throw a halogen onto a carbon, again, it's the same general idea. It's electronegative. It's going to take electron density away, which means it can act as a leaving group when the halogen is attached to a carbon. So in these cases, we're looking at C. Let's do CCl. Okay? If we're looking at our hydrogens, it will only act as an acid. If we go through and put that hydrogen next to an oxygen, that hydrogen will act as an acid. Okay? Unfortunately, oxygen has an extra tier of problems that come with it. That oxygen is electronegative and it has a lone pair of electrons. It's not so electronegative that it will hold those electrons like our halogens would. So instead of it acting as just an acid, as in the case of our halogens, our oxygen, or our OH, can act as an acid and as a base. So our oxygen acts as the base. Whoops, there's the base side. And the hydrogen that's attached to our oxygen can act as an acid. Okay? When we move to the NH, that bond is now, or our nitrogen has lost electronegativity so much that it's no longer strong enough to take the electrons away from hydrogen, which means we lose the acid functionality. And pretty much the only thing we've got left at that point is the lone pair on the nitrogen, and that gives us our base. Okay? So our nitrogens can pretty much only act as bases. We could jump into nucleophiles, but again, we're only looking at acids and bases here. Okay? When we move to the carbon-hydrogen bond, that bond is so nonpolar that we don't establish any charges, so we don't build a partial positive charge on the hydrogen, so we don't have an acid. We don't build a partial negative charge on the carbon, so we don't have a base. Okay? So when we're moving across the periodic table from, good thing I matched it up nicely up here, right to left, we end up decreasing in reactivity. We go from it being an acid in the case of our halogens, moving to ultimately neutral in the case of carbon. Okay? Question on those approximations or trends? Okay. We've then got the 4 main reactions that we've run this semester. Technically, Chapter 9 and 13 added 2 new types of reactions to them. I don't want to cloud that with more names with them, so we'll just treat those as separate reactions. So the 4 main types that you absolutely must know, your acid-base reactions, substitution, elimination, and addition reactions. Okay? So given an overall reaction, can you tell me which reaction occurred, which reaction type fits? Okay? Within that, you should be able to identify the things that have changed, identify bonds broken and bonds formed. That can help you determine what mechanisms are happening. It can also help you determine what type of reaction occurred. Okay? So real quickly, what type of reaction happened in the first one? We've got an acid-base reaction. The next one. Next one. And the last one. So it sounds like no one's going to get that question wrong, right?
Right.
Okay. So it's again, but looking for those differences. Okay, why is that top one an acid-base reaction? What changed? Okay, this bond was broken, that oxygen-hydrogen bond, because if we look to the product, we no longer see that oxygen-hydrogen bond. Where did the hydrogen bond or hydrogen atom go? To the nitrogen. What changed in the process of this reaction? The location of a hydrogen atom. Or rather, we can take that a step further. It's not just a hydrogen atom, it's a hydrogen ion. What reaction transfers hydrogen ions? Acid-base. Does any other part of that reaction matter? No. Focus on what the big bulk changes are, and that can help you identify the reactions happening. We move to the next one. What bond was broken? What bond was formed? Carbon-iodine bond broke, and the bond that formed? Carbon-chlorine. Okay? So we can immediately eliminate the acid-base reaction because there's no hydrogen transferred. Okay? What type of reaction occurred, or what physically changed? We took the chlorine and we put it on in place of, or substituted it, the other way, substituted it on our carbon and replaced it, or it replaced the iodine. Okay? Or we could say the iodine was substituted by our chloride, hence substitution. Okay? What happens in the next one? What bonds were broken? What bonds were formed? Iodine bond was absolutely broken. Okay, we'll notice that there's an H plus floating around, which seems a bit odd. So we probably had to break another bond. Where was that other bond? We've got a hydrogen. We could try and evaluate what bonds were formed. Okay, we could say that the double bond was formed. Let's just leave it at that. We'll say that the double bond was formed. Okay, so what type of reaction occurred here? This one gets a little bit more complex because we could say a hydrogen was exchanged. Hydrogen was transferred. But is that the only thing that happened? No. So it can't be an acid-base reaction. Something else occurred at the same time. What was the something else? Formation of that double bond. So we have elimination. Okay? So the structure doesn't matter. Evaluate the things that changed. Okay? That is guaranteed something that you can expect to show up on the exam. I can clutter it with a whole bunch of other junk. The junk is irrelevant to the overall problem. Only look at what changed in the course of the reaction. Okay? Last one, even though it looks kind of stupid. What bonds were broken in the last one? Broke the pi bond. What else did we break? That weird one, right? What other bonds did we form? We formed 2 new weird ones, right? Right. Of our reaction types, how many of them form 2 new bonds? Which would suggest we're seeing 2 new bonds happen around a double bond. We're looking at an addition reaction. The rest of it doesn't matter. Only focused on what changes. This is why throughout the whole semester I keep going back to identifying the bonds broken and the bonds formed. Because if you can zero in on just what changed, that allows you to be able to see what's happening. Everything else is there just to confuse you. Okay? And that's all biochemistry does. Okay? The structures are nowhere near as simple. You're just going to see more and more confusing things. Yes? Sorry, I didn't hear that. So, as far as identifying reactions, I don't need you to go into the details of SN1 or SN2. Okay? When identifying the reactions, these are the 4 main classifications. I do expect you to be able to identify different mechanisms. The question format will be different. Okay? In fact, that might even be on the next slide. There we go. Okay? So given certain conditions, for instance, your substrate, nucleophile, leaving group, and solvent, can you determine what mechanism should occur? Okay? So given an individual reaction, what is your end result? Okay? So if you see a substrate that has a primary alkyl halide, which substitution reaction would you expect? SN2, because the SN2 favors or doesn't want steric hindrance. A primary alkyl halide matches very little steric hindrance. Okay? So being able to pull at those individual structures, so again, identify what things changed in the course of the reaction, and then being able to predict what type of mechanism occurred. Where these tend to show up even more is when you're trying to predict products. Okay? So if you were given a reaction where you had to predict the products, what would your difference between your products come down to between the SN2 and the SN1? Stereochemistry. Okay? So I could ask a question that's going to push one mechanism over the other, and your answer to determine which mechanism was favored would have to show that stereochemistry. What if there is no stereochemistry? Doesn't matter which mechanism you go through. No. The only thing that's going to show up when we're looking at these individual mechanisms is that stereochemistry. So if you're just asked to predict the product, it doesn't matter which mechanism it goes through if there's no stereocenter. If there is a stereocenter, you have to be concerned about the mechanism. Okay? After substitution, we've got your elimination reactions. We've got the E1 and E2. Again, the same general idea. So given certain conditions, what ends up happening? Okay? We didn't look as much, yeah, I said that right. Look, can't talk this week. We didn't look as much in detail of the elimination reactions. I give up. But the same general idea applies. Okay? Given certain conditions, what reactions occur? How do those reactions occur? What would you expect to see if you were just asked to predict products? Would there be a difference between the E1 or E2 mechanism? There's no stereochemistry, sort of. We see trans versus cis, and in both cases, what do we end up seeing? Trans is our highest likelihood. Okay? So, given an elimination reaction, would we expect to be concerned about stereochemistry with our eliminations? No. Okay? So if you're just predicting the products, it doesn't matter as long as it's an elimination. Okay? Within one caveat, whoops, which isn't on that next slide, what's the issue or our complication with our E1 mechanisms? Anybody remember that one? E1 mechanisms, almost guaranteed, run simultaneous with the SN1. So if you run an elimination reaction, you're expected to predict the products, and you think it's an E1 mechanism, what does that mean you also need to provide as a product? So you would expect the double bond from the E1, but if it's an E1 mechanism, you also get the substitution product. So you would also have to provide that, which is what you saw on that exam. I think that was exam 2 where that showed up. One of the questions had that show up with possible products. Yes?
I thought that for elimination, one of the things that you needed was heat.
So heat is something that you can add to it that helps favor the elimination, but it doesn't guarantee it. Okay? Other questions with this older stuff? That was about when I realized that we'd already summarized all this on older slides. Hi. Chapter 13, we're looking at our carbonyls. Broke it down into those individual sections. You've got your nomenclature with your ketones and aldehydes. You can tell I still haven't written in aldehydes yet. Okay. Your general reactivity. What do we mean by general reactivity? What's the reactivity of a carbonyl? We could look at it as the double bond, our pi bond, being very similar to the double bond of an alkene. But we said our carbonyls react slightly differently from our alkenes. How? What's the difference between a carbonyl and an alkene? The oxygen. What does the oxygen do to the pi electrons? It takes them more often. So instead of having an effectively neutral alkene structure, we end up with a very partially negative oxygen and a very partially positive carbon. What does that mean for our reactivity? What would we expect of our oxygen? I kind of see where you're going with that. It should be a little bit more reactive. I was referring more to our classifications. It's a Bronsted-Lowry base because it can donate its electrons to a hydrogen. What else could it do? If it's got electrons, whoops, it could donate those electrons to something other than a hydrogen. So we potentially have a Lewis base. Okay. What about the carbon? If it's partially positive, I heard someone say the definite or an extra one there. We could call it an electrophile. What else could we label it as? Lewis acid. How about a Bronsted-Lowry acid? No, why not? Because the positive carbon is not a positive hydrogen. Okay? So that's the idea of identifying your general reactivity. This is something that we've been doing periodically with every single functional group, trying to look at them and evaluate that functionality. What chemistry can we immediately see coming out of them without actually doing any individual reactions? Okay? This is something I fully expect you to be able to do on the final. Okay? So every single functional group we've covered this semester, you should make sure that you can identify its general reactivity, whether it's a Bronsted-Lowry base, acid, or Lewis base or acid. Yes?
Is the oxygen a nucleophile?
We could also label the oxygen as a nucleophile. Why can we do that? What's the definition of a nucleophile? It's an electron donor. Well, can oxygen act as an electron donor? It's negatively charged, yeah. Okay? So those 6 definitions I had you memorize at the beginning of the semester, and they've showed up on every single test. Might also consider that showing up on the final. Just maybe. Okay? Once you've got the general reactivity, it then moves into the chemistry. Okay? In general, our carbonyls react primarily as electrophiles. That carbon tends to be a lot more reactive because it's missing the electron density, and our oxygen, because it's electronegative, isn't all that willing to share its electrons. Okay? So when we're focusing in on the chemistry, we're really addressing how the carbonyl can react with nucleophiles. And we said there were 3 different types. We actually added one at the very end, talked briefly about it. I want to make sure we come back to it. We can have hydrogen as a nucleophile. Pretty sure I've got that summary slide in there in a second, or in there. So we've got those 4 possible reactions. Carbon as a nucleophile. If it's carbon, okay, we have to get a negatively charged carbon. That's not the easiest thing to do. So we have to use the named reaction, a Grignard reaction. We're adding magnesium metal to the reaction. Magnesium shuttles its electrons over to the carbon. We get that negatively charged carbon. Okay, now we have a carbon nucleophile. That can then react with our electrophilic carbonyl. Okay? Our nitrogen, one of the better nucleophiles, at least of this pair or this set, because it has that electron density. Okay, already, we don't have to do any fancy stuff to it. It can go through and react with that positive carbonyl. We said that one was an important one to evaluate because that's ultimately how we're generating amino acids, our peptide bonds, the backbone of all of our proteins. Okay? The last, or second to last one was oxygen. That's where we saw our acetals and hemiacetals. Those play huge roles in biochemistry. Pretty much all reactions kind of revolve around those. Carbohydrates are all linked together through acetal bonds. Okay? So, or hemiacetal bonds, sorry. And then hydrogen acting as a nucleophile. How can we get hydrogen to act as a nucleophile? What charge would it need to be? We'd have to get hydrogen negative. How easy is it to get hydrogen negative? Not really, because it's so small. It's not very easy to get that electron density localized on an individual atom. We tried it before. We had hydrogen or hydride show up in previous reactions when we looked at our alcohol chemistry. And we did that with sodium hydride. Problem with sodium hydride, how did the hydrogen act in that case? As a base. It did not act as a nucleophile. So how do we get it to act as a nucleophile here? Instead of pairing it up with a sodium atom, we pair it up with boron. Okay? Boron's happy with just 3 groups of electrons, which means that 4th group of electrons tends to sit with the hydrogen, and that's how we generate our hydride nucleophile. Okay? So we get some very interesting chemistry coming out of this species. Ultimately, you're responsible for realizing that this reagent supplies hydride and it reacts with the electrophilic carbon. Okay? When we looked at our Grignard, so I got it all there. We went through and looked at a couple different carbonyls. If we had R groups or if we had hydrogens attached, that ended up changing what type of alcohol we generated at the end of it. Okay? You're responsible for realizing that pattern. I don't expect you to be able to make the Grignard reagent. Remember, we spent a decent amount of time looking at the mechanism for making the Grignard reagent, making that nucleophilic carbon. Okay, how do we make that guy? You're responsible for realizing what it would look like in a reaction, which would be carbon, magnesium, bromide. Where is that negative held in that new drawing? It's in that bond between the carbon and the magnesium. Carbon is more electronegative than the magnesium, substantially so. So it will take the electrons away from the magnesium. That's where we get our nucleophile from. Okay? We had nitrogen reacting as a nucleophile with our carbonyl.
Those are all tertiary.
Thank you. I didn't fix this either. Remember the copy-paste error? That one was secondary. This last one is primary. Okay, we'll leave that hang for a little bit so you can copy that. Okay, if we start with an aldehyde, one of those R groups is a hydrogen, which means when we move to the product, we only have 2 carbons attached to our alcoholic carbon, which gives us a secondary. Okay. If we start with formaldehyde, we get rid of both R groups and make them hydrogens. Now when we move to the product, the only carbon that we've got attached to our alcohol is the carbon nucleophile, which means by definition it's going to have to be a primary alcohol. Okay? Thanks for reminding me of that one. With our nitrogen acting as a nucleophile, we go through and generate an imine, which is a fancy way of saying a carbonyl, except instead of an oxygen, it's a nitrogen. It's the same thing. Okay? That nitrogen is a little bit different from our carbonyl in that nitrogen can have 3 bonds instead of the 2 from oxygen, which means we can have some random R group hanging off the side, okay, or an extra hydrogen. That changes the chemistry of the imine, makes it a little bit different from our carbonyl. We can get some more interesting things once we've made that. You don't have to worry so much about that. You're more concerned about following the arrows. So I don't have any arrows on there. So if you remember when we talked about it the first time, this was probably one of the lectures that didn't record, drawing out individual arrows. So you should be able to predict what shows up in the first box. So if I drew out this on an exam, what would you draw on the first box? Everybody agree? Shaking your head. Why do you not agree?
Plus
Nitrogen's got to be positively charged. Okay? Would that do anything for our next step? What would happen in our next step? Could we add arrows now to what's in our box to make it to the next step? What changed? So what bond was made to move to our product? Carbon, nitrogen, right? Okay, what charge is the carbon in our starting material? Where is that carbon? Attached to the oxygen. What partial charge is on that carbon? Oops. So it's partially positive, which would mean the nitrogen to make our product, right in there, if this carbon was positive, what charge does that nitrogen need to be? Negative. So let's go back to our starting material. What charge is the nitrogen? So if we go back to the previous box, what charge is the nitrogen? Positive. You sure you can add arrows to the structure to move to the next structure?
No.
Can't. Your nitrogen's not negative. Okay? That reaction can't physically work. Okay? We don't have the prerequisite items necessary to make that bond. Okay? To get that bond to form, the nitrogen needs to have some electrons. The carbon should be missing them. We can go through and look. Our carbon is definitely missing electrons. Our nitrogen also missing them. So what happens when I bring the nitrogen near the carbon? They repel away. What happens? No reaction. So can we add arrows to it? No. Okay, so let's switch it up, and instead of drawing that in our initial box, the initial box we drew exactly what the arrows showed. The arrows that we initially drew were those productive to go through the rest of the reaction. No, because we couldn't make it through the next step. Okay. So what if instead this is what was drawn in the box? Almost. Can we add arrows to our box to make it to the right? What charge did our carbon need to be? Needed to be positive. What charge is our carbon in our box? Partially positive because of that carbonyl. Okay. What charge does our nitrogen need to be? Negative. What charge is our nitrogen in our box? Neutral. Does it have a partial charge? Why is it partially negative? So one reason, we've got the lone pairs. Next reason, nitrogen is more electronegative than carbon and hydrogen. So our nitrogen does have that negative charge, which means we do have the matching piece to be able to progress across. So now what we have to do is add the arrows to our structure. Where should our arrows start? What was that? Okay, we can start them at the double bond. Where do we want to move those electrons? Why towards the oxygen? Oxygen is more electronegative and it's formally positive. Oxygen doesn't want to be positive, so it steals electrons from where it can get them. That pi bond's a good place. That carbon becomes now positive. How can we stabilize it? The electrons from our nitrogen. Okay? Exactly right. Okay. Exactly right. Not negative on negative, but you'd have too many electrons around the carbon. Okay? Get the idea? So the intent is to add arrows where you can actually propagate something forward. If you can't propagate forward, don't force it. It ultimately means that you screwed up. Okay? Which in this case, who screwed up? That was actually kind of my fault. Okay? Because the first arrows I drew were wrong. It didn't make sense. What arrows should have been added to our first structure? Okay. So the intent is to use your mechanistic arrows to solve reactions. If they're provided to you, do what your arrows show. Okay? And try to not do things that don't make physical sense. In our previous situation, our nitrogen was positive. It needed to be negative to satisfy our product. Okay? Yes?
Can you assume since oxygen is more electronegative than nitrogen, that kind of a little bond to oxygen?
It's a dangerous thing to look at. Do you really want to hear the answer on that? Okay. Comes back to resonance. It's going to be the best answer for that. Okay. Nitrogen is less electronegative, which means it's more willing to share its electrons. Nitrogen's the better base. Okay. So, the next part of this is what you would see in a lot of the homework questions, or what most of the homework questions asked for. What we did here is we aminated our carbonyl, because we turned the carbonyl into a nitrogen, okay, or turned the oxygen into a nitrogen. So we did an amination reaction. Okay, I don't know why they don't call it an immination, but amination reaction. Okay. What's the textbook then say to do? Or add as an extra step? They call it a reductive amination. So far, all we've done is aminated. If we want to reduce, what does a reduction do? Reduces the number of electronegative bonds and replaces them with hydrogens. So if I wanted to reduce this, what do I need to add? I need to add H2. Just gonna draw it like that. Just H2? We have to add one of the catalysts. Why? H2 is too small to react on its own with the double bond. We have to have that catalyst in there to help initiate, and we could end up with our reductive amination. Okay? Questions on that? Did I miss a carbon?
No. Do we really need to do the reductive part? Or is
For this case, no. I'm just trying to clarify the homework. Okay. Oxygen with a carbonyl. So if we had oxygen as a nucleophile, we've got all sorts of reactions going on here. Depending on that oxygen source, if the oxygen is coming from water, then what we end up with is a hydrate. If the oxygen is coming from an alcohol, we end up first with a hemiacetal, then ultimately an acetal. Okay? So you need to be able to recognize and find or define acetals, hemiacetals, hydrates, or just not applicable. And then also be able to look both forwards and backwards on either trying to make a carbonyl from the acetal, what pieces fall out of it, or to go from the carbonyl to the acetal, what pieces do you need to put into it to make that reaction occur. Okay? So that's our finding, our carbonyl, which is our electrophile, and our alcohol is the nucleophile in this case. And then feasibility in the steps of the mechanism, which we just talked about with the nitrogen as our nucleophile. Okay? We looked at two possible mechanisms. We can go through a basic mechanism. The basic mechanism stopped at the hemiacetal. Why did it stop at the hemiacetal and not continue to react? We still have a wickedly strong, good nucleophile. Why would it still not attack and substitute out? So what we're asking is, why is this last step not likely? What were our reasons? OH minus would be one of the other, whoops. Oh, it didn't go. Good. OH minus is a leaving group, or would be the leaving group. How good of a leaving group is OH minus? It's pretty awful, so we wouldn't expect that reaction to occur. Why else? What type of mechanism would that go by? What changed as we moved from our reactant to our product? What bonds were broken? Carbon-oxygen bond. What bond was made? Which type of reaction matches that bond breaking and making pattern? Our substitution reaction. Which mechanism? SN1 or SN2? SN2 because strong nucleophile. You said the other important part of this. If it's an SN2 mechanism, okay, what's the issue with this? This approximates a tertiary substrate. Does the SN2 allow tertiary substitutions? No. Okay? So two really big reasons why this step does not progress forwards on its own. We'd have to try and go through a different mechanism to make the acetal. Okay? Notice, what did we do here? Bonds breaking and making to figure out what type of reaction occurred in that last step. So you're still going back to those same patterns and trying to find out what's happening in each stage. The more productive one, if we want to make an acetal, is to do it under acid conditions. That involves a big, long mechanism, which I don't particularly want to go through again, but I'll have to tomorrow when I record it again. Going beginning to end, it's how that individual reaction works, each of those individual steps along the way. Okay? Won't go into them in too much detail, but let's try and address each step, classify it. What type of reaction is the first step? Acid-base. We're looking at the making and breaking, or the exchange of hydrogen. So it's an acid-base step. What happens in the next step? Admittedly, this is a harder one, because we didn't really do this one. We break the carbonyl, and we made that bond. So it's actually a really tricky one. It would be kind of the first step of what mechanism? Yeah, an addition reaction. Okay? So it would be step one of an addition. Okay, what happened in the next step? Make and break. What bond was broken? What bond? Oh, what bond was made? We didn't even make a bond. Oh, because it's not shown. What bond was made? What changed? The location of a hydrogen atom, which would mean? What happened in the next step? Bond broken, bond not clearly shown, but bond made. Again, acid-base. Final step, or third to final step. Again, kind of a weird one. Okay, we've got, I guess we could say, a leaving group leaving. What's happening in the very next step? So what we've got here is step one of which mechanism? SN1. How do you know it's SN1? Because you form the carbocation. The next one is step two of an SN1. Very last step, what changed? Hydrogen versus, again, not balanced. Oh, I didn't even show it. Let's just say H+. We have an acid-base reaction again. Okay. So evaluating each step of the reaction can be helpful to try and determine what type of reaction occurred and how many arrows you should be showing in an individual reaction. Okay? It almost never fails when looking at this reaction, somebody tries to show all of these arrows happening in a single step. Okay? I'm sure you can fit all of those arrows in a single step. That doesn't mean it makes physical sense. Okay? Break it into as small as steps as individually possible and work from there. Okay? Last thing I want to address on this slide is the summary on the far right. we're looking at the overall reaction shifting from the carbonyl to the hemiacetal, and then from the hemiacetal to our acetal. Okay? So to go from the carbonyl to the acetal, what do you need? I was hoping you weren't going to say it that way. We've got an alcohol. To take it to the hemiacetal, if I want to go all the way to the acetal, I need a second molecule, a second alcohol. Okay? What if I want to go from the acetal to the carbonyl? What do I need? I need water. Okay? Depending under what conditions we run it, either acid or base, you might see an addition of either acid or base, depending on what you're trying to do. Okay? Questions about our oxygen nucleophiles? Okay. Here's that redox of our carbonyls. Our sodium borohydride, that hydrogen can act as a nucleophile and react with our carbon. There's our new hydrogen bond. Okay, we can follow that up and just acidify and add an extra hydrogen to it, to the alcohol. Okay, so if you see sodium borohydride, all you're doing is converting a carbonyl to an alcohol. Okay, the carbonyls you can convert will be aldehydes or ketones. You don't have to worry about any others because I won't test you on any of the others. Okay. Yes?
I thought, didn't that reaction do all of the double bonds involved?
So this is one of the things that's nice about sodium borohydride. It only does carbonyls. If we wanted to do a reduction and reduce everything, what should we use? H2 and palladium, nickel, or platinum. Okay? So that takes everything out of the situation. But if I only want to reduce the carbonyl, that's when I have to use something like sodium borohydride. Okay? And that will just react with our carbonyls. Okay? Oxidations, you should be familiar with those because we've done those now a couple times. Okay, so there's nothing particularly new there. What the heck? The weird chemistry of our carbonyls, we can actually make that hydrogen kind of acidic. Okay, why is that hydrogen acidic? If we take that off, what do we generate? A negative charge on that carbon. Can carbon hold a negative charge very well? No, so we would immediately say not acidic, right? Except what can we do with that negative charge? Nine-letter words. We've got resonance. Push the electron density around, and we can put that negative charge onto the oxygen. It's a little bit better there, and since we kicked off H+ floating around in solution, we can have that pick up, and we end up with our final form. Okay? Known as the keto-enol tautomerization. It is an important one for biochemistry. A lot of synthetic chemists tend to use it too. Okay? I just want you to be aware that we can make that hydrogen acidic, and this tautomerization is possible. Okay? After that, we've got our arenes, which is looking at our aromatic rings. You need to be able to identify if it is aromatic or not. That follows these rules. Okay? I even nicely crossed out that rule 3 that you don't have to worry about. If I'm asking you, you can assume it's planar. Okay? Because I don't have an easy way to help you visualize if it's planar or not. Okay? So we'll just immediately eliminate that choice. So it has to be cyclic. It has to have a p-like orbital, which meant that it has to have an actual p orbital, or It could be sp3 hybridized, in which case it doesn't have a p orbital, but it also has a lone pair. The lone pair on an sp3, one lone pair on an sp3 atom can act as a pair of electrons and be donated into the ring. Okay? So that can count as a p-like orbital if you have a lone pair in an sp3 atom. Okay? After that, we've got all of the reagents. Okay? There are 5 of them that you need to know for this exam. Okay? So ultimately what you need to know is that these electrophiles show up. Okay? And let's add a little box on this one. If we were going to box in the electrophile in each place, I guess really I only needed it on the last one. Okay? Those end up becoming the electrophiles. So given the reagent starting on the far left, if we mix those, we can generate the electrophile in red. That electrophile is what then reacts with our aromatic rings in the EAS substitution reaction. Huh? I didn't show any arrows. Oh, I see. Okay. So when you're trying to put on individual groups, so if you look at an aromatic ring and say I ask, how can you make this structure from benzene in any reagent you want? What should you react with benzene? There's a hint, the answer is up here. What's the new bond if you start with benzene? What new bond was made? This one here. In an EAS reaction, what does the aromatic ring act as? Acts as the nucleophile. So it needs to share electrons. So if we go back and take a look at our new bond, the carbon on our aromatic ring should be what charge? If it acts as the nucleophile, it needs to be negative, which means the carbon on the other end needs to be positive. Which of these reagents adds a positive carbon? The very bottom one does, but it also adds at the same time that oxygen. Do we have an oxygen in our product? No. So the bottom one doesn't work. So the middle one works, but the middle one just says R. What's R? Anything we want. So what's the anything we want? There we go, where our carbon would be positive. We can't just add that reagent. We have to come up with how we made that electrophile. How do we make it? Go back to the starting material. Right? Now when we mix benzene with, what is that, isopropyl chloride and aluminum trichloride, we make our final product. Okay? Identify the bonds that break and are formed in the process of the reaction. And that can help you find these and identify these pieces. Okay? Questions about that? I will do one more example with the next sheet's electrophiles. Let's say we wanted to make nitrobenzene from benzene. What do we add? What's the new bond? Our nitro. What charge does the nitro have to be? Has to be positive because the aromatic ring acts as the nucleophile, which means the nitro needs to be positive. Which of these reagents gives us a negative or a positive nitrogen? The top one. And it also gives us at the same time 2 oxygens. There we go. Do it all in one fell swoop. So what reagents do we need to add? HNO3 with H2SO4. Okay? Identify your bonds made and broken, and that can help you process these problems.
So on the test, we do something like that, but would it like do a box in the middle and say what do you
Yes.
what reagent do you need?
So the formatting on the test, we've seen this problem before. It would probably be grouped with a bunch of others where it's predict the product, reactant, or reagent. It's typically the referring. This would be the reagent. You would have to supply HNO3 and H2SO4. If instead you had this, wouldn't say reactant, but you'd see the box. What would you put in the box? Put in our benzene. Or the last possible permutation. What's the product? Okay? Makes sense? Okay. Almost perfectly timed. This kind of summarizes everything. The title isn't very good on this, so I would kind of ignore that. But this summarizes all the different changes that you can get with your benzene rings. So when we go through and change benzene, okay, so that's ultimately our 0 point when we've got just hydrogens on it. If I want to make the reaction go faster, I need to make the benzene be more nucleophilic. To be more nucleophilic, it needs to be more negative. So somehow or another, I have to get more electrons into this. The only way I can do that is I swap out a hydrogen for a different atom. Okay? In the case that we've got up here, I kept them generic. We're swapping out that atom for atom X. In the top case, atom X has more electrons than a hydrogen. How do you know it has more electrons than hydrogen? Lone pair is the easiest way to do it. Okay, but what if it was this, and there was our benzene ring? We have to evaluate the charge on that carbon. Is there anything taking electron density away from the carbon? No. So what we're comparing is ultimately a carbon atom to a hydrogen atom. What's the difference? Doesn't have anything to do with electronegativity. All we're concerned about is, does it have more or less electrons than a hydrogen? It has more because it can't really get smaller than a carbon atom. So if we're comparing atom to atom, that carbon has more electrons than a hydrogen atom, which would then classify it under atom X. Okay? Where atom X has more electrons than hydrogen. If atom X is classified as having more electrons than a hydrogen, that ring is now activated. Okay, so we get 2 big conclusions from identifying that information. That ring is now activated. If it's activated, will we expect it to react faster or slower? Faster, because it's activated. Typically what activated means. Okay? What position is activated? So where would we expect the substitution to occur on an activated ring? The para or ortho positions. It's an or. Okay, so we could potentially see both of them reacting. As far as we're concerned for this class, because I'm not going to push this too far, you can pretty much ignore the ortho. Okay? The para reacts faster because there's less steric hindrance. The ortho is blocked by atom X. So if we try to move the electrons out, have our benzene ring act as a nucleophile, it bumps into the electrons of atom X and prevents the ortho substitution, or at least limits it a little bit. Okay? Depending on the size of atom X, it may completely prevent it, or it may still allow it to occur. Okay? For instance, stick with the CH3 as one option versus which one would we expect more ortho substitution to occur in? Left or right? The left, because there's less steric hindrance around it. Okay, what is that steric hindrance? In the case of the one on the left, we're looking at hydrogen atoms coming off of the carbon. In the case on the right, what's coming off? Carbons and officially hydrogens as well. CH3 is coming off, blocking those ortho positions. Okay. The last case that we can get is if atom X has less electrons than a hydrogen. The only way that we can get less electrons than a hydrogen atom is if our atom is positive. It does not have to be formally positive. Okay? You may not see a formal charge of a positive. So we'll evaluate what? Yes, so we could look at induction, or we could look at resonance. So when you look at your individual structure, look at that atom and see what's attached to it. See if it can generate partial positive charge, okay, or formal positive charge. If it can, that means it has less electrons than a hydrogen atom. Hydrogen comes in with 1 electron. If we get less electrons, it has to be positive. Okay? If atom X has less electrons than hydrogen, our group is now known as a deactivator, which means what about the speed of that EAS reaction? Should react slower. The only position left to react is the meta position. Okay? That's what all of those questions are going to end up addressing. So you can memorize your para-directing for your activators and your meta-directing for your deactivators. Almost guaranteed you'll see a question that will work for memorization on that. But I can guarantee you right now you will also have to prove it for at least one problem. How would you prove that it goes to the para versus the meta? You look at the sigma structures of your mechanism, which is ultimately looking at resonance. Okay? So draw out your mechanism for these reactions. Make sure that you understand them, because you will be asked to evaluate the resonance structures of your intermediates in these reactions. Okay? I think there are a few more review slides here. Oh, by a few more, there's one. And since it's my favorite, I guess we'll go back to it. Bonds and forces, it all comes back to applying these. The differences in electronegativity. Those differences in electronegativity allow you to find partial positive and negative charges. So make sure that you can identify what each of your bond types are, what each of the force types are. Okay? That allows you to find reactivity. It also allows you to predict something about melting points and boiling points. Okay? And I didn't check too carefully, but I think all of the last 3 exams had questions about melting points and boiling points. Okay? Maybe one of them I missed. Okay? So it's, again, another common question type that you can expect on the exam. And it's all coming back to the application of those bonds. Okay? Bonds and forces. Okay? So those are all the slides that I've got for review. I'm glad I didn't add any more to it. Do you have any questions? Anything you want me to directly cover? Yes?
I just have a question. Is there anything we should have made with our kit before we come in for the final?
So you are allowed a model kit. I would recommend, as I did with any of the other ones, drawing or building a cyclohexane. And in particular, I'd probably make it a methyl cyclohexane. And then off of that methyl, I would add as many different colors as you could get. So I think you've got white, red, blue, something like that. Okay. This works twofold because you get the cyclohexane, which can allow you to do your chair flips and hopefully allow you to see it so you can draw it a little bit better. And then it also allows you to set up with a chiral center. Okay? So all you'd have to do is really quickly break this bond and this bond off, and now you've got a chiral atom right on that methyl. Okay? Where you've got red, blue, white, and black for the carbon. Okay? That should allow you to answer any kind of chirality question. You'd have to break and move bonds around to make sure that your little model represents accurately what's drawn, but it's at least built. Okay? You don't have to worry about taking things apart. The stockroom, as far as I know, still will rent out model kits or loan out model kits, so you can grab that before the exam. I'll try if I remember to grab 3 or 4 of them, so I've got a few spares. Other questions? Nothing? Yeah, you still get a cheat sheet front and back on the cheat sheet. I guess I can add that on here, just in case someone decides to read over it. Anything else? Okay. If I don't see you on Friday,